I'm Afeefah Siddique, and I'm presenting the physics of theme park swings and G-force. So, it's physics day at the theme park, and you're there with your grandmother for the first time, and she's excited, and she wants to go on a ride. You love her, and you want to choose the safest ride. You see the swings, and you think, hey, this looks safe. And then your brain suddenly says, stop. Remember when you looked at that YouTube video of that one person flying off the swings mid-air? You decide to turn to physics to make sure that grandma does not go flying. You start by identifying the concepts involved. You get out your stopwatch and measuring tape and ask grandma a few questions, and you figure out some quick facts. She gets dizzy at 45 revolutions per minute, swing slants at 30 degrees, the swing cable is 5 meters long, and the distance from the central shaft to the swing cable is 3 meters long. This is what it looks like. The image on the left shows us our values that we have just recorded, and the image on the right is just a free body diagram that shows us all forces involved and also has included the calculation of the radius of the swing. So the force due to circular motion acts along the horizontal direction, which is balanced by the horizontal tension in the cable. The weight of the person and seat are balanced by the vertical tension in the cable. The time of revolution is calculated by knowing the angular velocity of rotation. The centripetal force is caused by the horizontal tension in the cable. Along the x-axis, the forces are given as follows. The centripetal force equals t sine theta, which is also mv squared over r, and we set that equal to each other. Forces on the y-axis are mg equals t cosine theta, and here the weight of the person and seat are balanced by the vertical tension. G is acceleration due to gravity, and m is mass. We divide these two equations, and we find that tan theta equals v squared over rg, v squared equals rg tan theta. We know that the speed in circular motion is radius times angular velocity. We square the equation on both sides, and we can substitute this equation into our previous equation, and we find rg tan theta equals r squared times angular velocity squared. We can simplify this further to find angular velocity, and we know that frequency and angular velocity relate, so we have angular velocity equals 2 times pi times the frequency. We can substitute this into our equation, and we find that the square root of g times tan theta over r equals 2 pi frequency. We rearrange this equation to find the frequency, and we also know that the time of revolution is 1 over the frequency. We substitute our equation for frequency into this time equation, and we find that time is equal to 2 pi times the square root of r over g tan theta. We can substitute in our values, which is our radius, our angle, and our gravity. And we find that time is actually 6.2 seconds for one rotation, which means that per minute we have 9.67, almost 10 revolutions per minute. Your grandmother wonders why you are taking so long to agree to go on this ride with her, and you tell her that you're just wondering if this ride will be safe for her. She then reminds you that she went through astronaut training when she was younger and can survive 9 Gs. She starts to give you information about G-force and their effects on the human body. Here's some examples of G-force. In the first problem, we can calculate G-force experienced by a driver of a car with an average radius of 750 feet of the car. And we find that we can use the acceleration equals v squared over r, plug in our values, and we find the acceleration of the car is 151 feet per second squared. Divide that by the acceleration due to gravity, which is 32 feet per second squared, and we find that the driver experiences 4.74 Gs. In the second problem, your grandmother is telling you about the training she went through at the research center in Mountain View, California, and how they determined how many Gs that they were going to put on the astronauts. So given that the radius is 29 feet per the apparatus, and the centripetal acceleration is 19.6 g's. If the angular velocity represents the rotation rate, acceleration equals radius times angular velocity squared, then we know that the angular velocity, or the rotation rate, is 0.7419 revolutions per second. And we see that comparing this problem to the problem before of the swing, that as the radius increases of the object, so does the RPM to maintain the g-force. So finally, you decide to go on Google and look up the largest g-force recorded for amusement park rides, and it turns out to be 6.3 Gs from Gold Reef City's Tower of Terror. You finally realize that the only person who won't survive this trip without getting dizzy is actually you. Here are my references. Thank you for watching. Please let me know how I can improve this video in the comments below.